common source amplifier with cascode current source as load. Here is the common source amplifier with an NMOS T1. Input voltage is provided to the gate of T1 and output is taken at the drain of T1, and a constant current source is connected as the load. When the constant current source is replaced by a cascode current source, which is shown here, we get common source amplifier with cascode current source as load. In my previous video, that is Microelectronics 3C, I have explained in detail about the cascode current source. So now I will assume you have complete understanding of the cascode current source. Here the voltage at the gate of T3, that is VG34, and the voltage at gate of T2, that is VG25, are constant voltages, and the voltage that is the drain of T4 is equal to the voltage at the drain of T3. For intuitive analysis, we can consider only the right hand part of the circuit, that is this part of the circuit, which is shown here. The gain of a common source amplifier is given by minus Gm times R out. Gm is the transconductance of the circuit. Gm of this circuit is given by the transconductance of the input transistor T1, that is minus Gm1. R out is the output impedance seen at the node V out. This is equal to the output impedance seen up parallel to the output impedance seen down. So R out down is nothing but the output impedance seen at the drain of the NMOS, which is equal to RDS1. R out up is the output impedance seen at the drain of T2 when T3 is present. This is equal to RDS3 times gain of T2, that is Gm2 RDS2. So R out up can be written as RDS3 into Gm2 RDS2. The effective R out will be R out down parallel to R out up, which is equal to RDS1 parallel to RDS3 Gm2 RDS2. Here we can observe that RDS1 is a small quantity compared to RDS2 RDS3 Gm2. So we can approximate R out to be equal to RDS1. So the gain of this circuit is given by minus Gm1 times RDS1. Even though the output impedance seen up is a higher value, because of a lower output impedance seen down, the effective output impedance, that is R out, is equal to RDS1. Voltage swing, input voltage range Vn. Here in this circuit, the current to T3 and T2 is fixed, which is decided by Iref. So the current, since the current to T3 and T2 is fixed and the input voltage VGS is fixed, so the VGS has only one fixed DC bias voltage. Hence, this circuit has only one DC bias voltage, which is not good. Output voltage V out. V out can not go to a maximum voltage of VDD because of the condition that the transistors T3 and T2 has to be in saturation. We know that condition for saturation of T2 is given by VDS2 has to be greater than VGS2 minus VTH2. So condition for this transistor is VDS2 minimum will be equal to VGS2 effective. And for T3, since the voltages Vx and Vy are same and the gate voltages are same, it can be proved that the gate voltage of T3 and the drain voltage of T3 are same, which means that T3 acts like a diode. So minimum voltage for T3 to be in saturation is nothing but VGS. So Vout maximum is given by VDD minus VGS3. So here VGS3 is written as VGS3 effective plus VTH plus VGS2 effective, that is the minimum voltage VDS2 voltage required for the transistor T2 to be in saturation. Vout minimum, Vout cannot go to ground because the transistor T1 has to be in saturation. So Vout minimum will be equal to VDS1 minimum. VDS1 minimum is nothing but VGS1 effective. So Vout minimum is